Okay, we are continuing on here in chapter 5. Hopefully. So last time we got into stoichiometry and really some basic stoichiometry type problems. And as we talked about, remember, pretty much the same 4 steps are followed. It all really starts with the balanced equation. And that's really important. If you don't have a balanced equation, pretty much the rest of your calculation is going to be wrong. So I would say probably 99% of the time you'll be given an equation. You just want to make sure, obviously, that is balanced. I would also say that probably if you see some numbers in the equation, it's probably balanced, I would assume. But definitely if you have an equation, you don't see any coefficients, you should definitely take a look at it to make sure that it is balanced. If you get maybe a probably lesser type problem where maybe you're given everything in words, as we talked about, you want to make sure you start with the right formulas first and then balance the equation. Then pretty much the opening step after that is to convert whatever they gave you to moles. And again, most commonly, you're usually given stuff in grams. And so that usually involves using the molar mass in the periodic table to convert your grams into moles. But in reality, you could be given any type of unit. So maybe it might require multiple sort of conversions, but ultimately where you want to stop is to get it into moles. And really the reason for that is that's pretty much how stoichiometry works. It works from the mole to mole relationship, which is basically the third step that you want to do here. And that comes from the balanced equation. And remember that when you have a balanced equation, basically we could just take the coefficients from the balanced equation and those represent the moles of each of those things. And really stoichiometry is nothing more than just a conversion factor. And instead of, like I said, sort of looking it up in a table or anything like that, you kind of get the conversion factor from the equation. So we could say, for example, 2 moles of A here equals 3 moles of B. And as we talked about last time, they are not equal to each other, obviously, in terms of numbers, but they are equal to each other in terms of, again, proportion that you kind of got to toss in there to get this reaction to really take place. And really from any sort of stoichiometric equality, which is what this is sometimes referred to, you could use it just like a normal equality and basically write 2 conversion factors. And obviously, like most conversion factors, you won't use them both in the problem. You will obviously just choose the one that you will need for your problem. How to decide, obviously, which ones to look for is also pretty straightforward. It's pretty much whatever they gave you in the problem is the one thing that you should look at. And then obviously whatever you're trying to find is the other one that you should look at. And that allows you really to go from something in the equation that you're not really interested in to somebody else in that equation that you are. And again, using this as a conversion factor to do that. The last step is sometimes needed, a lot of times needed, but maybe not needed all the time. But if you do step 3 correctly, which hopefully you should be sitting in units of moles at this point. So it's very common. We need to kind of convert it to some other unit. And also very common would be to convert it back to grams as a very common sort of outcome for that. So it really is in sort of basic stoichiometry problems, these 4 steps, and you just kind of go in order. If something's done for you, go forward, don't go backwards. The other important thing that we talked about is when we talk about sort of stoichiometry, sometimes people get under the impression that you have to do sort of like the mole to mole relationship sort of from one side to the other. And you can. So you could go from reactants to products in terms of relationships. You could also go from products back to reactants. But you don't have to cross over the arrow there. You could stay on the reactant side if you had 2 reactants and do the relationship between those guys. And you could also do it on the product side as well. If you had 2 products, you could do the relationship on the product side as well. So you don't have to necessarily cross the arrow when you're doing sort of stoichiometry. You can stay on one side or the other. The basis of it is just that mole to mole relationship. Any questions on any of those steps we talked about? Now, we also talked about a little bit about the idea of theoretical yield. Now, when we talk about theoretical yield, that is usually what you get as a result of doing a stoichiometry calculation and figuring out basically how much product did you produce. So a yield always has to be a product. So you can't have like a theoretical yield of a reactant or anything like that. but it's always some type of product. And as we'll talk about a little bit later on here, that's pretty much like your maximum product that you should be able to produce if everything went perfect in that particular reaction. Any questions on any of those steps there? Okay, so you might have another example or not, but we're going to kind of continue on here and go to the next sort of topic, which is a little sort of variation on stoichiometry problems. And these are sometimes referred to as limiting reagent problems. They're also sometimes referred to as limiting reactant problems. In most sort of reactions that occur, the reactants really don't sort of get used up at the same rate, if you will. There's always some type of reactant that gets used up first. So there's always some reactant that gets used up first. And that is what is known as the limiting reagent. And there's also obviously one reactant that usually you got plenty of, and that's usually the other guy, which is the reactant you have plenty of. That's what is known as the excess reagent. Or again, the excess reactant. So when we talk about limiting reagents, the idea there is, there's going to be something in terms on the reactant side that gets used up first. Now, why is that important when you're trying to figure out something like how much product that you would make? So for example, if we obviously just took A plus B to make A and B, clearly in this case, in order to make our product, which is A and B together, we basically need both of those guys. So let's just say, for example, A here was our limiting reagent. That means at some period of time, we're pretty much going to run out of A. And if we should hit that period of time where we run out of A, is there any chance of making any product at this point? We can't, right? Because we're basically missing A. So in this case, and in all cases, whenever you have a limiting reagent, it is the most important guy there because it really determines how much product you can make. So the limiting reagent problems can be done a multitude of ways, but we'll kind of do it the same way that we did the previous type ones. You basically could follow the same sort of steps that we did on a basic stoichiometry problem, which I just listed there, which obviously is balance the equation, convert to moles, do your mole to mole relationship, and moles to some other unit. So one approach, which is what we'll do in this particular lecture here, I think, is pretty much you start out just like normal. You balance the equation, you convert whatever they gave you to moles, and right about here is a good place to figure out, which one is the limiting reagent. So there's sort of an additional step that you have to do right around there to sort of figure out which one's the limiting reagent. Once you're able to make that determination, then you pretty much can pick up the rest of the steps just like normal. And you would want to pick up the rest of the steps using the limiting reagent to then do the mole to mole relationship, and then basically how much product that you produce there and whatever units that you're looking for. Any questions on that so far? Okay. So as I mentioned before, there's also the excess reagent. And sometimes in these problems as well, they will ask you something. Because it's the excess reagent, you have plenty of it. It does not get used up in the reaction. You actually have some of it left over when the reaction is done. So a very common sort of question sometimes that's asked is, how much of that excess reagent is still hanging around at the end of the reaction? So those are sort of questions that you could ask. But how do you know that it is a limiting reagent problem versus just a regular sort of stoichiometry problem? The way that you can know is if you are given enough information to get to moles of each reactant, that is pretty much how you know it is a limiting reagent problem. That is also how you know somewhere along the way you need to do that. Now, if you think about some of the examples that we did previous to this last time, if you look back at those examples, pretty much you're only given one piece of information, like, hey, you started with this many grams of this guy or this many grams of this guy. You weren't given enough information to figure out the moles of each reactant. But whenever you see that you have enough information, whatever they give you, that you can do some type of conversion to get to moles of each of them, that definitely is a signal that you need to, at some point, figure out the limiting reagent. And here, if we look at sort of exercise buddies, we need a guy and a girl here to do that. So clearly we can see at some point here, we are going to use up the guys here, and that would mean that our guys are limiting reagent. We also could see, just based on stoichiometry, that, you know, we have enough to use up 3 of the females here. And we could also answer the question here, since these would be our excess reagent, we would have obviously 2 left over. So these are very common type questions that, you know, you're sometimes asked. And the most common is obviously how much product that you would form here, if I spit that out, in this case. So let's take a look at an equation like this and talk about sort of how can we determine, you know, which one's the limiting reagent and which one is the excess reagent. So we have an equation up here and it's balanced, which is sort of our first step. So we're good there. We see our stoichiometry happening here. And again, in this case, 1 mole of sulfur reacts with 3 moles of F2 to form 1 mole of SF6. So let's just say, for example, we had a problem such as this, where we are taking 4 moles of sulfur and we're going to react it with 20 moles of F2. So clearly we know this is a limiting reagent problem because I definitely have moles of sulfur, which is a reactant, and I have moles of F2, which is a reactant. In this case, they were nice enough just to start us at moles. They could have started us at grams, but here we're just starting at moles. So that tells me it's a limiting reagent problem. Now, what we're going to do here, so basically step number 2 is kind of done for us. It's already in moles, whatever they gave us. So here's the part where we need to figure out which one's the limiting reagent. And again, there's a few different ways you can approach these problems. So we're just going to do one way here. So one way is you would do a simple stoichiometry problem to basically answer the question of this, which is, if I want to use up all of my sulfur, how much fluorine would I need? So you're basically going to do just a small little calculation here to go, I want to use up all one of the reactants, how much of the other reactants I need. Just so we're clear, what we are starting with of both of those guys is given to us here, 4 moles of sulfur and 20 moles of F2. So that's basically our starting amount. What we're going to try to figure out now is how much do we need of the fluorine to use up all the sulfur. So to do that, we would start with the moles of sulfur that we're starting with, which is 4. We would do the stoichiometry between these 2 guys, and we could see for every 1 mole of sulfur, we get 3 moles of F2. So just a very simple little stoichiometry calculation here. Moles of sulfur go on the bottom to cancel. 3 moles of F2 go up on top. Moles of sulfur cancel. Tells me, without the use of a calculator, maybe a bad move, but we'll go with it. 12 moles of F2 is needed. First off, any questions on the little calculation here? So we're just doing a calculation between the 2 reactants. And basically what that calculation is saying, if I want to use up everything of sulfur, I need to toss in there 12 moles of fluorine. So this is the part where you can now determine, you know, which one's your excess reagent, which one's your limiting reagent, by simply comparing numbers. I just figured out that I needed 12 moles. And if I look back to where I am starting with 20 moles of it. Do I have enough moles? If I need 12 and I got 20, I do have enough, right? 20 is bigger than 12, so I have plenty of moles of it. Because I have enough of the F2, what that means is the F2 is going to be my excess reagent because I have enough. The beauty of this is if you can figure out one, by default, the other guy is the other thing. So that would tell me that the sulfur here is actually my limiting reagent in this particular case. Any questions on that so far? Now, you may be asking, do you have to pick always like the second guy? You don't. You could pick either one. So if I did the opposite calculation, which once again, you don't have to do both calculations, but you could choose either one. If I did the opposite, which is if I want to use up all of my fluorine, how much sulfur do I need? We would do basically a similar calculation, but we would start with fluorine, which is 20 moles. We would use our same mole to mole relationship, which is 1 mole sulfur on top and 3 moles of F2 on the bottom. Gives me 20 divided by 3, gives me 6.67 moles of sulfur is needed. So if I chose the other reagent, did the very similar calculation, when I look at this, I need 6.67 moles of sulfur. I am starting with 4 moles. Do I have enough sulfur in this case? I don't. So it doesn't give you the same number, but it tells you the same thing. Because I don't have enough sulfur in that case, if I chose that calculation, it would once again tell me that that is the limiting reagent and that is the excess reagent. Again, you don't necessarily have to do both, but you could choose either one you want. It doesn't really matter which one you choose. You just need to do a simple little calculation like that to figure it out. Any questions on that? Yeah.
So, for example, if you were to ask us that on the test, how would you write it as far as
if you were asked what the limiting reagent was in this example, it would be the sulfur. And if you're asked what the excess reagent is, it would be the F2. Would be, yeah. No, you wouldn't need the amount. It would be so this question would be more of a stoichiometry question. So the question would actually be asking how much product would you produce. So in order to get to pretty much how much product, you got to kind of do this step and this type of thing. So we'll kind of finish it out like that. So the actual question would be something like, you know, how many moles or grams of this guy would you have produced? So once we did either one of these calculations, we now know that the sulfur is the limiting reagent. So the important thing is to make sure that you actually go back to the starting amount of your sulfur or your limiting reagent and use that for the calculation. And if we wanted to do that, we can now look and do 4 moles of sulfur, which was our limiting reagent. We can look at the equation now between sulfur and our product, which is ultimately what the question is going to probably ask. And we see it's a 1-to-1 relationship. So that makes it pretty simple. It's 1 mole of sulfur gives us 1 mole of SF6, I believe, right? And those cancel, which means that we would produce in this case 4 moles of SF6, which would in theory be our theoretical yield in moles, which then we could do actually the 4th step. So this would be like the 3rd step in our stoichiometry calculation here after we figured out the limiting reagent. We could go to our 4th step, which would be convert that guy into how many grams that would be. And we would use the molar mass of SF6, which is like 3207 for the sulfur and 6 times 19 for the fluorine over moles. Those guys would cancel, and it looks like maybe, oops. So that's like 146-ish grams per mole. And times it out by 4 means we would get something in this made up example of like 584 grams of SF6. If I punch that in right one more time, just to make sure. Bless you. So we got 584 grams of SF6, which would be our theoretical yield in grams. So these are really what the problem would be, which I think was your actual question, which is basically it'll just be like a question like how much product would you produce? And it won't in a lot of questions and like blinking lights go, hey, this is like a limiting reagent problem or anything like that. So that's why you have to be able to recognize it like we were here, that we were given enough information to get the moles of both of the reactants. So that's the additional thing that you just has to kind of know to do in these type of stoichiometry problems. Other questions? Okay. The other thing that sometimes asked is like how much of the excess reagent would be left over. And we can actually figure that out as well. We could actually figure it out based on our original calculation here, since we chose correctly. We figured out really with this original calculation that we would need 12 moles of the F2 to use up all the sulfur, which is our limiting reagent. We are starting with 20 moles of it. So we also could pretty simply figure out how much of that excess reagents left over, which in this case was the F2. We started with 20 moles. We needed 12 moles, which means at the end of this reaction, all the sulfur should be gone, but we should have about 8 moles of F2 left over at this point. And obviously you could also convert that into grams if you want to know how many grams would be left over using the molar mass. So sometimes you get, if you're asked that type of question, you get a pretty lucky deal here. If you kind of chose the right reagent to figure out your limiting reagent with there, you can do that. If the other guy was a limiting reagent, you would have had to maybe go back and do this calculation, if you chose differently. But, it's also a very common question. It's like how much of that excess is left over. Any questions on any of that there? All right. All right. And that's pretty much what we just talked about. So I'll just kind of scroll it across there in case you like to watch it later. All right. So why don't we try one and see how you do here? All right, so 6.8 grams of iron is reacted with 9.34 grams of sulfur. Which of the two is the limiting reagent, and how much of the FeS will be formed? So some info here. Iron is 5585, and sulfur is 3207. All right, so take a minute, see what you come up with. So we're given this problem, 6.83 grams of iron are allowed to react with 9.34 grams of sulfur. We pretty much want to know how much product's being formed. If they weren't nice enough to kind of ask that question, we would know that it is a limiting reagent problem because they gave us grams of iron, which clearly we could get some moles from. And we're also given grams of sulfur, which we could clearly get the moles from. So again, if they didn't tell you limiting reagent, that is what should sort of point out to you that this is a limiting reagent problem. And somewhere along the way, you got to figure that part out. Which one is the limiting reagent to help you do that? And again, that is exactly how you could kind of, first off, just straight up determine that it is that. We're going to do basically our same steps. So we're going to balance the equation, which looks like it is balanced. So that's good. We're then going to really do the second step, which is just convert whatever they gave us to moles. In this case, we actually have two numbers to do. So we got our 6.83 grams of iron using the molar mass from the periodic table from iron, which is 5585. And we would also do our conversion of our sulfur, which is 9.34 grams of sulfur, also using the molar mass there from the periodic table, 3207 grams per mole of sulfur, gets us 0.83 divided by 585, gives us like a 0.122 moles of iron. And 9.34 divided by 3207 gets us a 0.291 moles of sulfur. Any questions up to that point? Again, this is just basically the same stuff that we did before. It's at this point, because we know we need to do a limiting reagent or figure out which one it is. This is the part where we can, again, do our limiting reagent calculation. A reminder that these guys right here are pretty much our starting amount of each of these guys. So in my case, what I'm going to calculate is how much sulfur I need to use up all the iron in this case. So how much sulfur is needed to use up all the iron. So starting with my iron, which I want to use up, 0.122 moles of iron, going to the balanced equation, which as we can see is a 1-to-1 relationship between those two in the balanced equation. We would use our stoichiometry here, 1 mole of iron on the bottom, 1 mole of sulfur up on top. Those guys cancel. And it tells us that we would need to put in there 0.122 moles of sulfur is needed. Questions on that calculation there? This is the point where we look at how much sulfur we need to how much sulfur we're starting with, which is right above it. And do I have enough sulfur in this case? I do. I have enough, right? I only need 0.122 to use up all the iron. I am starting with 0.29 of it, which is more. So I have enough. That basically means that it is the sulfur, which would be my excess reagent. And by process of elimination, that means in this case, it is the iron, which is the limiting reagent. Any questions on how we determine that there? Obviously, if you went to compare and you did not have enough, it would be like we saw on the other one, it would be the limiting. In this case, we are good. So what that means is now we have everything we need to pretty much pick back up with our stoichiometry steps, which now is the mole to mole relationship between always the limiting reagent and the product in this case. So the third step would be we would want to start with the starting amount here of our limiting reagent, which is 0.122 moles of iron. Going back to the equation, if I go the right way, there it is. It is also a 1-to-1 relationship. That's convenient between the iron and the product there. So once again, from the equation, we see we have 1 mole of iron gives us 1 mole of our product. The moles of iron cancel, and we get 0.122 moles of iron 2 sulfide, which again would be our theoretical yield in moles. But do we want the answer here in moles? We want it in grams, right? So we do just go on to step number 4 here, and we're going to convert our moles into grams, which is 0.122 moles of iron 2 sulfide. In order to do that, I need to go to the periodic table, right, and get the molar mass of those two guys together, which is pretty much just add these guys together, right? And that would get us 5585 plus 3207 gets us 87.92 grams per mole would be the molar mass of iron 2 sulfide. So we'll use that as our conversion factor here. Since we want grams at the end, we want to put grams up on top and moles on the bottom. These guys are going to cancel, and we will end up with about 10.7 grams of iron 2 sulfide should be produced, and that would be our theoretical yield in grams. So hopefully you can kind of see it's really the same 4 steps. You just got to take that little shortcut there in the middle to basically figure out which one is the limiting reagent. Any questions on any of those steps there? While we're here, we could also again figure out how much of the excess reagent would be left over. So in our case, since we chose kind of luckily there, we actually got the excess reagent in our calculation. So we can figure out how much of the excess reagent is left over because based on our original calculation, we needed 0.122, and we are starting with 0.291 moles of it. So if we were asked how much of that's left over, I'm just going to flip the page so I got somewhere to write, I think. So the leftover sulfur in this case, which is our excess reagent, again would be what we started with there, 0.291 minus what we needed was 0.122 moles. So started, needed. And if we did that there, so 0.291 minus 0.122, 0.122, yep, gives us 0.169 moles of sulfur is left over. And once again, you could, if you wanted to, simply convert that into grams by using the molar mass from the periodic table of sulfur. And roughly we got something like 5.42 grams of sulfur that's left over. We started with about 9.3 grams, right? We used about 4-ish grams, and we got about 5 grams of the sulfur left over when this reaction is done. Any questions on any of that calculation? So like I said before, there are sort of multiple ways you could do limiting reagent problems. This is one approach that you could do. Just to show you maybe another very common sort of approach that you might like better, since this problem does have a lot of like stoichiometry going on. Everybody good? Can I go flip it? So the other approach that's very commonly taught in terms of limiting reagent problems is you basically just do 2 separate calculations. One starting with one of the reactants to the product, and the other one starting with the other reactant to the product. And you figure out how much product each one would make. So if we did that, sort of an alternative approach, you could take 6.83 grams of iron, and you would actually just follow the same 4 steps that we did before. We would convert this into moles using the molar mass, 5585 grams per mole of iron. And if we did that, obviously we would get our moles that we started with, 6.83 divided by 5585, gets you our 0.122 moles of iron. We then would do our stoichiometry between iron and our product, which gives us 0.122 moles of iron to sulfide, and carrying that over using our molar mass that we got up there on top, 8792 grams per mole, gives us about 10.7 grams of our FES. Now you could do it all in one step without getting an answer in between. So we'll do that for the other guy, 9.34 grams of sulfur, converting to moles, 32.07 grams per mole of sulfur, doing our mole to mole relationship, 1 mole of sulfur, 1 mole of our product, and our molar mass of 87.92 grams per mole of FES. So again, as we talked about last time, you don't have to necessarily get an answer at each step. You could just do one big calculation there. And if you did that guy, what you would end up with is, that's it, about 25.6 grams of iron 2 sulfide. So the sulfur gave us 25 grams or so of the product. The iron gave us 10.7 grams of the product. When you do this type of problem like this, you always take the smaller one, yeah? So the smaller one would be both your limiting reagent and the amount that you yielded. So that is the alternative approach, just do 2 separate calculations. Whichever one produces a smaller amount of product is both your theoretical yield, and whatever you started with would be your limiting reagent, and the other guy would be your excess reagent. So that's an alternative approach. If you like that way better, you could do that as well. There's like 2 other ways you could do it as well. So there's multiple ways you could kind of do it. But those are the 2 common ways that we just kind of talked about there. Any questions on either way? Yes. Okay. All right. All right, so why don't you give this a go, see what you come up with. How much product are we going to form here, starting with 622.7 grams of NH3 that react with 1241 grams of CO2. And there's the molar mass of everybody. So these are the molar masses from the periodic table, so you don't have to calculate them. So that should help. Yeah, I think it is with the 2. It should be balanced. There's 2 nitrogens, 6 hydrogens, got 4 and 2, 6 on the right, 1 carbon, and 2 oxygens on each side. Yep. Okay, so let's take a look, see how you're doing. So once again, if they didn't tell you that, which often they don't in problems, we do know it's limiting reagent because we do see we're given grams of NH3. We're also given grams of our CO2. And obviously, since we have grams given to us, we could get some moles. So again, that is the key to know that you do need to figure it out. The equation is balanced. So really, we could roll into just converting some moles here. So number 2 step there would be to convert to moles. So we got 622.7 grams of NH3. If it wasn't given to you, obviously you would go to the periodic table to get the 1703 grams per mole. And that gets us 622.7 divided by 1703, roughly 36.565 moles of NH3. We're also going to convert to moles our other guy, which is our CO2. That's a 1241 grams of CO2. Once again, you would also go to the periodic table if it wasn't given to you to get the molar mass there of the 4401 for the CO2. That gives us 1241 divided by 4401 gets us a 28.198 moles of CO2. Again, this is, if you want to remember, basically your starting amount of each of those guys. Any questions up to there? At this point, we're going to figure out the limiting reagent. So here, I'm going to figure out how much CO2 is needed. So basically what I'm going to do is start with my NH3, and I want to use up all my NH3. So looking at the equation, it is a 2-to-1 relationship between the NH3 and the CO2. So using that stoichiometry there, 2 moles of NH3 on the bottom, 1 mole of CO2 up on top would tell me I got 36.565 divided by 2. About 18.28 moles of CO2 is needed. That again is what we're going to use to compare to our starting amount of CO2. And do we have enough CO2 in this case? We do. So that means we do have enough. So the CO2 would be our excess reagent. And our NH3 here would be our limiting reagent by default. Any questions up to that point? Now that we took our little detour here to figure out how much, which one's the limiting reagent, we're going to go back and use that limiting reagent to figure out how much product we're going to produce. So in this case, starting with our 36.565. So 36.565 moles. Or not. So go that way, do that, do that. just hit everything on the screen here. Here we go. There we go. All right. All right, so that is moles of our NH3. We're going to use the mole to mole relationship from the equation, which looking at it is 2 moles of NH3 to our product here, which is 1 mole. And that would be what we would want to use. So 2 moles of NH3, 1 mole of our product there, which I think is something like that, I think. And 36.565 divided by 2 gets us 18.28 moles of our product. H2 2CO. And we could then convert it into grams by using the molar mass that they gave us, which was 6006 in this case. So using our molar mass here of 6006, which again, if not given to you to the periodic tables where you would get that, would get us roughly 1098 grams of our product here. And that would be technically our theoretical yield here in this particular case. Any questions on that part there? Any questions on any of those steps? It could just be rounding if you're like if you're very close, it might just be some rounding, you know, if you round a little bit differently. If you're dramatically different, then somebody's wrong. Could be me, I don't know, but let's see. Everybody else get this? Good, yeah, okay. All right, any questions on linear reagent type problems here? I'm gonna skip the excess part of it because I didn't put it up there, so I don't know if anybody did it or not, but we'll skip that part. All right, let's then talk about yields of reactions. We sort of talked about an important yield already, which is the theoretical yield. The theoretical yield is pretty much what we've been calculating. It is really the maximum yield that you could get in a chemical reaction. It is based off of how much you start with of a reactant and how much product you should make if everything went correctly. Again, there was no side reactions. You didn't throw it on the floor, throw it in the trash can, dropped it all over the place, or anything of those nature. When you really physically do an experiment like this, that usually some of those things happen, hopefully not the dropping part, but you know, there are sometimes side reactions. Even just simply scooping things out of a beaker or a test tube, you can't get it all out no matter how much you try to scrape it out, so you lose some product along the way. So what we end up with is what is known as the actual yield. And when you physically kind of go do the experiment, and it is pretty much what the name implies, it's actually how much product you produce when you physically went and did that experiment. The good news in book problems is that is usually given to you. Yes. So that's usually given to you in book problem. If you're doing a lab, you need to figure out usually how much product did you made. That means that typically you would have to calculate the theoretical yield like we've been doing. So that could be a basic stoichiometry problem, or it could be sort of a limiting reagent type problem to calculate the theoretical yield. And when you put both of those yields together, it gives us an important yield when we do sort of reactions. And that is what is known as the percent yield. The percent yield is taking the actual yield divided by the theoretical and times it by 100. Here, you actually want a high number is good, as opposed to percent error where you want like a low number. Percent yield is a good number to be high, but not too high. You know, is it possible to get over 100%? The answer is it is possible, but it probably means you screwed up along the way. So it's not actually a good thing to get usually over 100%. A very common way people get over 100% when they do an experiment, say they made a solid and you put the solid on some filter paper and you filtered it and you have your solid on here and your paper is still kind of wet there and people don't wait for it to completely dry. They go weigh it, and then what you get is like mass that you think is your solid, but it's actually just the water on the filter paper, and you end up with like 140% and go, cool, I did 40% more work. I should get an A. And maybe you won't get that A because it's not such a good thing. So, in the 90s, really good, 80s, really good, as you obviously get lower and lower, not so good of a job there. If you got like a 20% yield, you might have been sleeping for 80% of that experiment there and lost half of it. So this is very common how we do it. So again, this is usually given to you in a problem, a textbook type problem. This is usually some way you got to calculate like we've been doing, and then obviously divide the two to get to times it by 100 to get to your percent yield. So let's try one more here to end the day and the week, not that one. Let's do this one, which is the same molar masses that we just used on the previous problem. So if you take 100 grams of ammonia and react it with 100 grams carbon dioxide, and you produce 120 grams of this guy, determine the percent yield. And again, use the same molar masses as the last example. It's the exact same equation and all that kind of stuff. So it was like 1703 for NH3. That was like 4401 for CO2 and 60-ish there for our last guy there. Okay, so since we're getting in, let's take a look here and see how you're doing. So first off, is this a limiting reagent problem? It is. Again, we're given the grams of ammonia, which means we could get the moles, and we're given the grams of CO2, which means we could also get the moles. So our equation is balanced. We're just going to kind of roll through like what we did before here. We're then going to convert what they gave us to moles. So 100 grams of NH3, again, using the molar mass from the periodic table to convert that. And 100 grams of CO2, using CO2's molar mass from the periodic table to convert that one. Going to get us for the NH3 5.872. And for the CO2, we will get something like 2.272 moles of CO2. Once again, this is basically our starting amounts of each of these guys. Any questions up to there? So again, since it is a limiting reagent problem, we're going to take the approach of just doing a little calculation to figure out. So here, I'm going to figure out how much CO2 is needed. And again, what we're figuring out is how much CO2 is needed to use up all of the NH3. So we will start with the NH3, which is 5.872 moles of NH3. From the equation, the stoichiometry, we can see for every 2 moles of NH3, which goes on the bottom, we get 1 mole of CO2. And again, that is the mole to mole relationship from the equation. That tells us that we do need, in terms of CO2, about 2.936 moles of CO2 is needed if I want to use up all my NH3. I then can compare it to the CO2 that's over here. And do I have enough? I do not have enough, right? Yes, sir. Question or? Always reactants, yeah. So always reactants when you're doing this type of stuff. And whichever one's the limiting will help you determine how much product you produce, yeah. Other questions? So because we don't have enough, in this case, it is the CO2 is the limiting reagent, and the excess reagent would be the NH3 in this case. Now that we've determined which one is our limiting reagent, we can now actually figure out how much product to make. Again, we want to make sure that we are using the starting amount, not the number over here. So we want to make sure we're using the starting amount of it. And I'll just flip the page here. So that's going to be 2.272 moles of CO2, which is our limiting. We can now do the mole to mole relationship between the CO2 and our product, which I believe is a 1-to-1 on that one, I think. CO2 to 1 mole of our product. And again, that comes from the balance equation. Those are going to cancel. That gives us 2.272 moles of our product, which again would technically be the theoretical yield in moles. But since our actual yield is given to us in grams, we do want to go and convert this one more step here to grams so everybody's in the same units here. And it was 60.06, I think, right? The molar mass there, 60.06 grams per mole. That moles are going to cancel and leaves us with approximately 136.5 grams of our product. And again, that would be our theoretical yield. Any questions on that there? Now, earlier, really the question is asking about percent yield, which is our actual divided by our theoretical times 100%. This is the actual yield. Like I said before, it's actually the value that's given to you. So the 120 that we see in there is the actual yield. What we just did was calculate the theoretical yield. So our percent yield in this case, actual divided by theoretical times 100%. Actual given to us, which was 120 grams, divided by our theoretical 136.5, times it by 100%. Going to yield us an 87.91% yield. Not terrible, not great, but not super bad. Any questions on any of those steps there? So very much like this problem, this is sort of how the problems are worded. Obviously, they usually don't mention like limiting reagents or excess reagents. And again, the actual yield, that 120 type number, is usually given to you in a textbook problem. Any questions on stoichiometry? Yes. All right, you run. Yeah. Yeah, so if you're asking about the percent yield, you absolutely could do moles divided by moles, grams. As long as they're the same unit, you could do any unit you want. So oftentimes, a lot of times the actual give it to you in grams. So that's usually why we kind of go to grams. But if you could absolutely do moles and moles, it's fine. As long as they're the same unit. Same one, yeah. Yeah, so the whole point of finding the limit range and all that is, as we did with that very simple explanation of A plus B gives you A and B, as soon as the limiting reagent's gone, there's no possible way to make any more product. So it is always the limiting reagent that determines how much product you form. And in our earlier problems where we did basic stoichiometry problems, where we were given reactants, it's assumed since you're only given one number that that's the limiting reagent. So that's why you didn't have to find it in those type of problems, and that the other guy would be the excess. So it's really only when you're given enough of both reagents that you have to yourself sort of figure out which one's the limiting. But in problems where it's just one, it's assumed that that is the limiting reagent. You have to figure it out. Other questions? All right, this wraps up chapter 5. That means